Today's lecture is a primer on large language models. We'll discuss just enough of the foundations of large language models to be able to thoughtfully implement them in production systems. I encourage you to do a much deeper dive on this important topic. The more you understand about language models, the more you'll be able to implement efficient, safe, and effective AI applications. The fine details of LLMs is outside the scope of this course, but my hope is that this lecture will provide just enough framing and context for our next lecture on LLM ops. Let's start by understanding what large language models actually do. Large language models are designed for next token prediction. This means that given a text prefix, the language model assigns probabilities to subsequent words and returns the words that are most likely to come next. Here's a concrete example to illustrate this. For the prefix, the most famous city in the US is, a properly trained model will assign higher probabilities to words like New York and Los Angeles than to completely unrelated words like Sharpie or laptop. This probability assignment is the fundamental operation that makes language models work. Modern large language models have been designed using transformer architectures, which are neural networks that process sequences of tokens in parallel. The key innovation that enables modern LLMs is the self attention mechanism. Before self attention became available, we used recurrent neural networks, or RNNs, for processing long text sequences. However, RNNs had several significant issues. They were very slow to train, and they suffered from vanishing gradient problems, which meant losing information as sequences got longer. LSTMs improved the situation, but still had considerable limitations. Transformer architectures take as input word embeddings that represent the input text. These input embeddings undergo several manipulations and transformations, and then we output embeddings which can be rehydrated as text. There are several standard steps that we take to prepare our input text. First, we use text normalization techniques like case folding and removing punctuation. Next comes tokenization, where we break text into words, subwords, or characters. In our tokenization step, we perform token ID mapping, where each token gets mapped to a vocabulary ID. After that, we create embeddings by converting tokens to high-dimensional vectors that represent the text's contextual semantic meaning. Finally, we add positional encodings to provide position information, either through explicit vectors or implicit placement. Once we have our input embeddings, we apply the self-attention mechanism. The self-attention mechanism is what determines relationships between different words and phrases in the input text. Here's how the self-attention process works. Each input embedding is multiplied by 3 learned weight matrices. This generates what we call query, key, and value vectors. The query vector helps the model ask which other words are relevant to me. The key vector provides labels that identify how words might be relevant to others. The value vector holds the actual word content information. We then calculate scores to determine how much each word should attend to other words in the sequence. We take the dot product of the query vector of one word with the key vectors of all of the words in the sequence. We normalize the scores by dividing by the square root of the key vector dimension, then pass this through a softmax function to obtain the attention weights. Weights give us insight into how strongly each word is connected to the others in the sequence. Once we have our weights, each vector is multiplied by its corresponding attention weight. The results are summed, producing a context-aware representation for each word. Encoder-decoder architectures are specialized kinds of transformer architectures. Let's examine how encoder-decoder architectures work within the transformer framework. The encoder processes input sequences into continuous representations that hold contextual information for each token. Here's how this works. First, we normalize the input sequence and tokenize it. Then we convert it to embeddings with positional encodings. Next, we apply the self-attention mechanism, where each token attends to every other token in the sequence. The output is a series of embedding vectors in a new vector space that represents the entire input sequence. The decoder takes the encoder's output and generates new content token by token. There are two important attention mechanisms that work within decoders. The first is masked self-attention, where each position can only attend to earlier positions in the output sequence. The second is cross-attention, which lets the decoder focus on relevant parts of the input sequence using the encoder embeddings. It's worth noting that many recent LLMs, like the GPT series, use decoder-only architectures. These models focus primarily on generating output sequences directly from input without requiring complex encoding layers. In these architectures, the input sequence processing includes generating embeddings and positional encodings before being passed to the decoder. The decoder then uses a masked self-attention mechanism to generate predictions for each token based on the previously generated tokens. When we talk about training a large language model, or any machine learning or deep learning model, we mean that we are modifying the parameters of the model. Training is the process of finding optimal internal model states that best achieve the task we've set up. When we use the model for inference, we mean that the model is used only for generating some predicted output. Inference does not involve modifying the model's parameters. When training a transformer model, we use batches of input sequences that are sampled from a training dataset. For each input, there's a corresponding target sequence. That batch input is fed to the transformer, and then the transformer predicts the output sequences. The differences between predicted and target sequences is measured using a loss function. Gradients of the loss are calculated, and an optimizer uses them to update the transformer's parameters. This is repeated until the transformer converges to a certain level of performance or until it has been pre-trained on a pre-specified number of tokens. There are three main categories of transformer architectures. First, we have decoder-only models, such as the GPT series. These are pre-trained on language modeling tasks, where the target sequence is a shifted version of the input sequence. For example, if the input is the cat sat on, the target would be cat sat on mat. Second, we have encoder-only models, like BERT, which stands for Bidirectional Encoder Representation from Transformers. These models are trained by corrupting input sequences and then reconstructing them. For instance, the input might be the mask sat on the mat, and the output would be the cat sat on the mat. Third, we have encoder decoder architectures, which are used for tasks like neural machine translation, question answering, and text summarization. These models encode the input and then decode it to the target language or format. An important concept to understand is context length, which refers to the number of tokens a model can remember and use for the next token prediction. RNNs and LSTMs had very short context windows, while modern transformers can handle entire PDFs worth of text. However, there are important trade offs to consider. Longer context allows for more complex relationships to be understood, but it requires significantly more computational resources and memory to operate effectively. Let's very briefly explore the history of transformer based language models. The first major milestone was GPT-1 in 2018, which was the first generative pre-trained transformer created by OpenAI. This was a decoder-only model trained on only a few billion words. The key innovation of GPT-1 was that it combined transformers with unsupervised pre-training followed by supervised fine-tuning, creating what we called a semi-supervised approach. GPT-1 also introduced task-aware input transformations for question answering without requiring task-specific data formatting. Shortly after, in late 2018 and early 2019, we saw the release of BERT, which used an encoder-only architecture and provided high-quality pre-trained vectors. BERT spawned several variants, including character BERT, sentence BERT, and sequence BERT. GPT-2 came in 2019 and represented a significant leap forward with an order of magnitude more data than GPT-1. It was trained on 45 million Reddit pages with karma greater than 3, representing 40 gigabytes of data and 1.5 billion parameters. The key achievement of GPT-2 was zero-shot learning on various tasks without explicit training. While it didn't outperform state-of-the-art models in specific tasks, it showed remarkable generalization abilities. The jump to GPT-3 and 3.5 was dramatic in terms of scale. While GPT-2 had 1.5 billion parameters, GPT-3 expanded to 175 billion parameters. This scale difference enabled several new capabilities: the ability to store and recall huge amounts of information, generate more coherent responses, and demonstrate better generalization across task ranges. The key innovation during this period was instruction tuning using reinforcement learning from human feedback, or RLHF. InstructGPT, with only 1.3 billion parameters, achieved better human evaluations than vanilla GPT-3. This demonstrated that external tools and techniques can improve models beyond just scaling parameters. GPT-4 brought several key features to the table. It became multimodal, meaning it can process images and text while producing text output. It has a context window of 128,000 tokens, which is roughly 128,000 words, with a maximum output of approximately 4,000 tokens. GPT-4 can approximate complex tasks, including mathematics, coding, machine vision, law, and psychology. 2025 saw exciting advancements in LLMs, mostly characterized by multimodal support and new reasoning techniques. OpenAI released the GPT-5 model, as well as open-weight models, GPT-OSS 120B and GPT-OSS 20B. DeepSeek released the V3.1 model, which can switch between thinking mode for complex reasoning and non-thinking mode for faster direct responses. DeepSeek also released R1, specifically designed for high level problem solving in areas such as financial analysis, complex mathematics, and automated theorem proving. Alibaba released Qwen 3 series, a mixture of experts model series that reportedly beat GPT-4o and DeepSeek v3 on most public benchmarks while using less compute. Meta released Llama 4, which includes natively multimodal models like Llama 4 Scout and Llama 4 Maverick. Llama 4 Scout has a context window of up to 10 million tokens. Anthropic released the Claude 4 family, Opus 4 and Sonnet 4, which integrate multiple reasoning approaches, including extended thinking mode. Mistral AI released Mistral Medium 3, a multimodal model. And lastly, Google's advances included the Gemini 2.5 series, which is updated for enhanced problem solving and native multimodal understanding. Gemini features a multimodal encoder-decoder architecture with a mixture of experts approach, where multiple specialized models are aggregated for complex outputs. Staying abreast of LLM developments can be exhausting. Luckily, the community maintains several leaderboards that compare model performance across many kinds of benchmarks. I encourage you to explore the Artificial Analysis.ai leaderboard, the Vellum LLM leaderboard, and the LLM Arena leaderboard to stay abreast of model performance. Let's explore how we can take these foundation models and adapt them for specific use cases through fine-tuning. Foundation models are trained on huge amounts of diverse, unlabeled data for next token prediction. Their task is to predict the next token given some previous context. Given that they're trained on a large and general distribution of data, foundation models are inherently designed to be good at sampling from this large distribution. The pre-training part of LLM creation is by far the most expensive in terms of time and amount of compute, which positions these foundation models to be optimized to be as generalizable as possible. Given that foundation models are highly generalizable, we benefit greatly from customizing these foundation models for specific tasks and specific knowledge domains. To do this, we use a process called fine-tuning. There are several approaches to fine-tuning foundation models. Supervised fine-tuning involves training the model on task-specific demonstration datasets. Instruction tuning takes a different approach by providing instructions for the model to follow. Examples include telling the model to summarize this text, write code for X, or write a poem. We then give feedback on the model's instruction following performance. Dialogue tuning focuses on fine-tuning using conversational data to improve the model's back and forth conversational abilities. Safety tuning is designed to mitigate risks from bias, discrimination, and toxic outputs. This process uses reinforcement learning from human feedback. As we mentioned in the last slide, supervised fine-tuning is when we train an LLM on a set of task-specific demonstration datasets, where performance is evaluated on domain-specific tasks. We show the model examples of the desired input-output format and update the internal parameters based on these examples. Each data point consists of an input, or a prompt, and a demonstration, which is the response we would like the foundation model to optimize for. For example, if we are using SFT for a model that is intended to summarize academic articles, we can use a dataset comprised of articles and then provide examples of summaries we want the model to provide when asked for a summary. Reinforcement learning from human feedback, or RLHF, is another kind of fine-tuning method. In RLHF, humans rank or rate different model outputs for the same prompt, for example, indicating which output is the most helpful. We then use this feedback to train what's called a reward model. This is a separate model that predicts what humans will prefer. The last step is to use reinforcement learning to fine-tune the original model to maximize the reward model scores. Due to the scale requirements of data needed for reinforcement learning, we're increasingly seeing AI in the loop approaches, where AI feedback is used instead of human feedback. Traditional fine-tuning updates billions of parameters in a model, which requires massive compute and memory. It also requires creating a full copy of the model for each task we are optimizing for. There are other risks with fine-tuning, including catastrophic forgetting of the original capabilities. One technique for fine-tuning that addresses these problems is parameter-efficient fine-tuning, or PEFT. PEFT refers to techniques that adapt large pre-trained models to specific tasks while updating only a small fraction of the parameters. Low-rank adaptation, or LoRA, is one such method. It freezes the original model weights and adds small trainable adapter matrices that learn low-rank updates. Instead of modifying a massive weight matrix, you learn two smaller matrices whose product approximates the change needed. Quantized low-rank adaptation, or QLoRa, is an extension of LoRa that makes fine-tuning even more memory efficient. We use quantization, which is the process of reducing the precision of numbers used to represent a model's parameters and computations, making the model smaller and faster with minimal accuracy loss. First, we load the pre-trained model using 4-bit precision instead of 16-bit or 32-bit precision. Then we add our adapter matrices, which remain in higher precision, like 16-bit. During training, the frozen 4-bit weights are dequantized for computation while gradients are calculated, but only the LoRa adapters are updated. We can optimize our interactions with these models through prompt engineering and sampling techniques. Prompt engineering involves providing clear instructions to LLMs in several ways. We can give specific examples, use keywords for emphasis, format input text to highlight important information, and provide background context that helps the model understand what we're asking. Prompt engineering comes in a few flavors. The first is few-shot prompting. This is when we provide the LLM a task description as well as a few carefully chosen examples to complete the task. For example, we may provide the LLM the names of 3 to 5 countries as well as their capital cities, and then ask it to generate the capital city for a country that isn't in the examples we gave it. Zero-shot prompting is when we provide a prompt directly to the LLM and include instructions as part of the prompt. Chain of thought prompting can be used to improve LLM's performance on a complex reasoning task. In chain of thought prompting, we provide a prompt that demonstrates how to solve similar problems using step by step reasoning. The LLM will then mimic our thought process using its own chain of thought for the new problem, breaking it down into smaller steps and explaining its reasoning. Sampling techniques allow us to control the quality, creativity, and diversity of model outputs. Remember that, at its core, an LLM is just trying to predict what the next most likely token will be, given some input. If we use greedy search sampling technique, the LLM will select the next token with the highest probability at each step. This is the simplest option for sampling, and it can produce repetitive and predictable output. Random sampling involves sampling from the probability distribution instead of always choosing the highest probability token. Each token is sampled proportionally to its predicted probability. This results in more creative but potentially nonsensical outputs. Temperature sampling adjusts the probability distribution using a temperature parameter. Higher temperature leads to more diversity and creativity, while lower temperature produces more conservative outputs that stick to high probability tokens. Top K sampling randomly selects from the top K most probable tokens, allowing us to control randomness by adjusting the K value. Top P sampling, sometimes called nucleus sampling, takes a different approach by sampling from a dynamic subset of tokens whose cumulative property adds up to P. This method adapts to the model's confidence level, meaning it favors more diversity when it's uncertain and focuses on a smaller set of highly probable words when it's confident. Best of n sampling generates n separate responses and selects the best according to predetermined metrics. This technique is particularly useful for short snippets or in situations requiring logic and reasoning. When working with LLMs in any system, whether it's enterprise-level support chatbots or in-terminal code assistants, we can optimize the performance of our LLMs. Combining prompt engineering with sampling techniques and correctly calibrated hyperparameters can greatly influence the LLM's response, making it more relevant, creative, and consistent for your needs. When building applications that serve many thousands or even millions of users, developers are always incentivized to reduce both cost and latency. This is no different in AI-powered applications. Balancing the time, money, and energy of serving a model with the model's overall performance is called the cost-performance trade-off. LLMs use significant compute resources, specifically memory and computation. To improve user experience, we focus on improving our inference services' memory and computation. Optimizing inference performance has become a significant priority for any technology company that serves AI capabilities. It's important to note that there is a trade-off between the quality of model response and latency and cost. If we improve the speed and cost of inference, we need to accept marginal drops in our model's accuracy. That may be acceptable for many or even most use cases, but could be disastrous in others. The latency versus throughput trade-off is equally important. Throughput refers to the system's ability to handle multiple requests efficiently. Better throughput on the same hardware reduces per request costs. For bulk inference applications, cost is more important than latency. However, for chat applications, latency reduction is critical for user experience. There are several techniques we can use to optimize inference performance. Model size reduction techniques include knowledge distillation, where a smaller model learns to mimic a larger one, and quantization, which reduces the precision of model weights to lower memory usage and speed up computation. Then there are techniques that are built to specifically try to preserve the quality of the model's output. Flash attention is an efficient attention mechanism that reduces memory usage and speeds up computation without sacrificing accuracy. Prefix caching is a method where we store the computed representations of previously processed tokens to avoid redundant calculations during inference. Speculative decoding involves generating multiple potential continuations of a sequence in parallel and selecting the most probable one, which can speed up response times. Batching and parallelization techniques allow us to process multiple requests simultaneously, improving throughput and reducing latency. Latency hiding is another useful technique where we stream results word by word while still processing the full response. This creates the appearance of faster response times even when the underlying processing time remains the same. It might come as a surprise, but not all large language models have the sole task of next token prediction. In fact, there are several kinds of tasks that we might want to use a large language model for. Natural language processing, or NLP, has a long history where language models were created to achieve a particular task. We had specific metrics and criteria that we used for evaluating how well our language model performed on those tasks. Information retrieval has a long and robust history. In fact, information retrieval had impressive results well before transformer models. A retrieval task is defined as given a query and a set of objects, retrieve the most relevant objects. Depending on the definition of relevant objects, subtasks can include question answering and recommendations. Semantic text similarity is another task. In semantic text similarity, we determine whether two samples of text, for example, sentences, have the same semantic meaning. Subtasks include text paraphrasing, duplication detection, and bytext mining. Text classification is where we classify objects into possible categories. Based on the number of labels, subtasks can include binary classification, multi-class classification, and multi-label classification. Clustering is a task where we cluster objects together according to the latent properties of the objects. Re-ranking is a task where we re-rank a set of objects based on a certain query. These days, it's common to conflate all of these tasks. Our current mental model of LLMs is one where the LLM achieves all these tasks at once, but that's not the reality of the underlying operations of LLMs. Recall that LLMs are trained to perform the task of next token prediction. In order to perform these other tasks, we need to augment our LLM with additional tools and context. Now let's explore one of the most important techniques for making language models more reliable and accurate: retrieval augmented generation, commonly known as RAG. RAG is a technique that combines information retrieval and text generation. The RAG process works by first retrieving relevant documents from a knowledge base, typically stored in a vector database. Next, we expand the original prompt to include those retrieved documents as context. Our LLM then generates a response using both the original query and the retrieved context information. The primary purpose of RAG is to provide a way to generate answers to domain-specific questions while reducing hallucinations. Providing specific context to foundation models is a way for the foundation model to incorporate domain-specific context that may not have been available in its original training data. While RAG doesn't eliminate hallucinations entirely, it significantly improves the accuracy and reliability of model responses. To implement RAG effectively, we have to have a way of searching through a knowledge base to find relevant documents. Vector search algorithms are the easiest way to do this. To create a knowledge base, you first create embeddings from your domain-specific documents and store them in a database. Then you use semantic similarity search techniques to find relevant context for user queries, ensuring that responses are grounded in your specific knowledge base. The way that we find documents that are semantically similar to the user query is by using vector search algorithms. Vector search algorithms are designed for high-dimensional embeddings. The goal is to find data points closest to each other in vector space and identify words or documents most similar to a given query. Several algorithms support this functionality, including approximate nearest neighbor, also known as ANN. ANN finds the closest points to a given point in a dataset within a small margin of error. Locality-sensitive hashing can be used when there's a large number of vectors to search through. LSH uses a hash function that maps similar items to the same hash bucket with high probability. It can quickly find all of the similar items to a given item by only looking at the candidate items in the same hash bucket, or an adjacent bucket. It can then do a linear search among those candidate pairs. KD trees is an algorithm that creates a decision boundary by computing the median of the values for the first dimension of a vector, then the second dimension, and so on. A ball tree algorithm creates buckets based on the radial distance of the data points from the center. Facebook AI Similarity Search, or FAISS, is one of the most popular vector search algorithms due to its ability to complete searches in sublinear time. It uses hierarchical navigable small world, or HNSW, which is a proximity graph with a hierarchical structure that performs efficient approximate nearest neighbor search, particularly in high-dimensional vector databases. Scalable approximate nearest neighbor, or SCAN, is a technique that uses approximate methods as well. It partitions the vectors into logical partitions or clusters, where semantically related items are grouped together. An operator can specify a distance measure to select the number of top partitions to consider for retrieval. A scoring step compares the original user query with all of the top partitions and selects the top k results to return. If creating embeddings for a knowledge base and implementing an efficient vector search algorithm sounds daunting and time consuming, you'll be glad to know that vector databases are built specifically to manage massive vectors, and many vector databases come with search algorithms built in. Generating embeddings of our knowledge base text can be done as part of our data ingestion pipeline, or, depending on the vector database, can be generated using built in embedding models that come pre shipped with the database. Whether you use your own or use a built in embedding model, the first step in RAG is to embed the relevant data points as vectors with fixed dimensions. The vectors in the database are augmented with metadata and tags, and indexed using whichever indexing algorithm is required for efficient search. An incoming query is embedded using the same embedding model, and then used to query and return a specific number of the most semantically similar results, along with their associated unembedded content and metadata. Vector databases will often let you choose between a small number of pre-shipped vector search algorithms for this query. Some databases provide caching and pre-filtering and post-filtering capabilities to further enhance the query speed and performance. Vector databases have surged in popularity over the last several years. There are both closed source, platform as a service vector databases, and also open source vector databases. Popular options include several key players in the market. Vertex AI is Google's vector database and RAG service. Pinecone is currently the most popular option, though it's not open source and can be expensive. Weaviate and ChromaDB are open source alternatives. When choosing a vector database, there are several considerations to keep in mind. Embedding mutation is a particular challenge, as embeddings change over time, especially after retraining models. Cost considerations become important because frequent updates can be expensive due to write operations. In many cases, you may need a combination of full text search and semantic search to achieve optimal results. Let's move on to discuss agents and how they fit into the broader system architecture for LLM applications. Agents are applications that attempt to achieve a goal by observing the world and acting upon it using the tools it has at its disposal. Agents can be autonomous and can be proactive in their approach to reaching their goal. Agents are designed to handle complex tasks that require multiple steps and interactions with various systems. They can manage workflows, make decisions based on context, and integrate with external tools and services to achieve their objectives. To do so, we program agents with specific cognitive architectures that comprise of behaviors, actions, and decisions. In the context of an agent, a model refers to the language model that will be used as the centralized decision maker for the agent's processes. The underlying model can be one or more language models capable of following instruction based reasoning and logic frameworks. The models can be general purpose, multimodal, or fine tuned for the specific environment and context in which we need to operate an agent. Agents serve as the intermediaries between users and models. Agents are built to achieve specific goals. These goals can be simple, such as answering a question or summarizing a document. They can also be complex, such as managing a multi step workflow or coordinating between multiple systems. Goals can be static, meaning they remain the same throughout the agent's operation, or dynamic, meaning they change based on new information or content. On their own, foundation models can't interact with the outside world. In order for our agents to be able to take actions in the world outside of the foundation model, we provide the agent with a set of tools to use. Tools are what allow an agent to interact with external data and services, enable web API operations, including get, post, and delete requests. Some examples of tools are microservices that update customer information in a database, or a function that can make a request to a weather data service to influence a travel recommendation. Tools are the way that agents access and process real world information, and they also empower more specialized systems like RAG. This foundation in LLMs, transformers, and system architecture prepares us for the engineering challenges of deploying and managing large language model systems in production environments. The next lecture will dive deeper into practical implementation details. Thanks so much for watching, and we'll see you next time.